Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer, although I have to say lately I've been doing more electrical engineering. I'm also a FileMaker, a certified FileMaker developer. I've done two important database modules for the reciprocal system. The reciprocal system Macrocosmos database and the reciprocal system Microcosmos database. Last week I did Galaxy clusters and groups. I showed you all the layout fields. This week, today, I'm going to show you the Galaxy layout, which is right here. Like most of the layouts in this system, you can add a new record. If there's some galaxy that you're interested in is not in the database, you just click that and you can add it in yourself. The form is what you see here. If you click Table, you get a list of the galaxy, the records in the file. Let's go back to Form. You can find any galaxy you want. You can sort. You can print the record or a group of records. You can revert if you've made a mistake, or you can delete the record. Okay, so let's look at the fields here. I'm going to actually let's go to the Milky Way. So I'm going to do find. I'm going to say Milky Way. Click off there, hit enter, and here it is. Okay, so the galaxy name is the first field, obviously Milky Way. There's no NGC or Messier for this because this is obviously our galaxy. The form number is normally going to be 1, but if you want to have multiple records for the same object, you would just increment the form number just to keep, just to let you know that the records are separate and not just mistakenly duplicated. Sometimes the references give rather astonishingly different values for certain of the properties, so you may want to have 2 or more records for a particular object if that's what you're studying. By the way, let's just take a look at the references. So let's go to Help. I'm going to go to More Help here. And here are the references down here. I'm just going to scroll through just to show you what's involved. Lots of references to Dewey B. Larson, who was my mentor, then, of course, to myself and previous papers. And then look at all the different physics textbooks, astrophysics textbooks. Just look at all this. Kenneth Lang's work, Astrophysical Formulae, is pretty important. Lots of these. The Carol Nosley book. Just look at all these. I had to use all these references to do the work to develop this database. Still got there. We go. 77 references. Alright, so let's go back here. Let's go back. Okay, now we're back to there. Let's go back to Galaxies. We're back to the Milky Way. Okay. Notice down here the parent object is the local group, so that makes sense. Star clusters, but we could list them all. I mean, that's just an option. Sometimes I didn't bother to put the parent object in there, but it's no big deal. The location here, generally for most objects in the database, it's J2000.0. The right ascension, hours, minutes, and seconds, you can see the number here. Declination in terms of degrees, minutes, and seconds. Galactic 1 or 2 coordinates of the nucleus and B. I usually don't use these, but if you do, you can put them in here. The total number of stars is estimated to be 200 billion. I think that's still pretty accurate. The gas mass is 1 times 10 to the 10th in terms of stars, I guess. Let's see. Now we have here show video or picture. You scroll down. These are sorted in descending order by date. And then we have the events like plurality of singularities, annotated galactic center. Let's see what else. Let's just take a look at that. When you click there, it'll go here. And here you can see the different things in the center. I galactic center, M20, M24, M23. And then, of course, you just click back on the Galaxies tab and you go right back. You can, of course, add more events here, and you can add more to the video or picture. These are more general, like general descriptions or videos. These would be specific happenings. But you can add your own, of course. Dimensions, I don't have arc minutes by arc minutes, but I do for many of the galaxies. Diameter is 23 kiloparsecs. Don't have the axis ratio here, but I do for some galaxies. Now here we have the radial velocity would be, of course, 0 and z0 because this is our galaxy. Rotational velocity is 220 kilometers per second. Rotational period is 2.459 times 10 to the 8th years. The distance would, of course, be 0 because it's our galaxy again. This would be relative to the CMBR. That's the cosmic microwave background radiation, 600 kilometers per second. Now we have the different types. The Hubble-Van Denburg system, S capital B small b. This is pretty complicated, and the different references give different values. You can also, if I missed one, you can edit this list and add, but I think it's pretty complete. The D. Van Coulier system is here again. Some of these are fairly certain and some aren't. And then Morgan's system. Again, you have to take a look at your astrophysics textbook to understand what that is. The CMBR energy density in ergs per centimeter squared is 0.4 times 10 to the minus 12. Cosmic ray energy density is 2 times e to the minus 12. Magnetic field is 2 times e to the minus 12, and turbine gas 0.5 times e to the minus 12. Galactic active class, galaxy active class, is relatively inactive as compared to many. Now look at all these choices you have. Lots of categories here. The quasars associated with it. Now let's come over to the luminosity. This is total bolometric, so that's the total in terms of the luminosity of the sun. 3.6 times 10 to the 10th. Ergs per second is 3.003 times 10 to the 43rd. And you can read the rest of these: optical, infrared, radio, ultraviolet, X-ray, gamma ray. Some of these just don't know at this point. And for optical, we have the ergs per centimeter squared. The mass in solar masses, we're assuming 200 times 10 to the 9th. Seems reasonable. That's in grams. The gravitational limits of the galaxy. The first gravitational limit, megaparsecs, is 0.495 megaparsecs. Within that gravitational limit, mass goes inward toward the center of the galaxy. Outside of it, it moves outward with the space-time progression, with gravitation subtracting from that. The second gravitational limit, megaparsecs, is 1834.623. That's the speed at which another object would be moving away from us at the speed of light. And so the total mass to luminosity ratio is 5.556. All right, now this is for spiral galaxies only, not elliptical or spheroidal. The radial extent, kiloparsecs, mass in solar masses, luminosity in solar units. So this is the bulge, that's kind of the nucleus. The spheroid section, the disk. This is kind of for a thick disk and for a thin disk. We have approximately 160 globular clusters and approximately 1,100 galactic clusters. Galaxy spiral arms, scutum at 5 kiloparsecs from galaxy center, Sagittarius, and so on. So like 3 arms here. And here's the, well, this has the mass to luminosity ratio for the different parts of the galaxy. And then the metallicity, which is the, the amount of iron versus the amount of hydrogen. Let's see what this says. if Fe over H is equal to -1, then iron has only 1/10 of its solar abundance, etc. So you can see the minus numbers here. Paranology is, I said, the local group. And then come down to the notes. You can, of course, add whatever notes you want. It's just, it's a little bit lengthy here. Well, let me just read it and see if we can. I think it's probably pretty helpful. References do not agree on the values such as mass and luminosity for our home galaxy. The values given should be considered tentative. So, I mean, yeah, I showed you all the references, over 70 references. Anyway, from The Unmysterious Universe, UM, page 51, spirals such as our Milky Way and the giant spheroids contain both type 1 and type 2 supernovae, which result from a different kind of stellar explosion that we examine in detail in chapter 16. Oh, I'm sorry, not the Unmysterious Universe, I mean the Universe of Motion. So sorry, UM means Universe of Motion. That's Stuart B. Larson's work in astrophysics. So Universe of Motion, page 148. The fact that the development of the spiral structure antedates the appearance of the second generation stars enables defining the general distribution of the stellar classes of the Milky Way galaxy in similar spirals, with the qualification, quote, except for strays from older systems, which has to be understood as attached to all statements in the discussion of stellar populations. We may say that the stars of the second and later generations, class 2C and later, are confined to the galactic disk, including the arms and the nucleus. The early first generation stars, class 1A, are distributed throughout the outer structure. They constitute practically the entire halo population. The mean sequence stars of the first generation, class 1B, occupy an intermediate position most prominently in the spiral arms. Okay, so Universe of Motion, page 197. As noted in that earlier discussion, the development theory indicates that galaxies as large as the Milky Way are pulling in not only a large amount of diffuse material, but also individual stars, globular clusters, and small galaxies. And again, the Universe of Motion, page 198, we can say that any galaxies within a distance of about 2 million light years of a galaxy as large as the Milky Way are in the process of being pulled in toward the galaxy and will eventually be captured. We can also say that any galaxy in the way to capture will experience structural distortion in the last stages of its approach. And page 199. If the Milky Way is not yet within the gravitational limit of M31, that's Andromeda, it certainly will be within that limit when the capture process is a little further along. In the meantime, the total mass of the various aggregates and diffuse matter between the major galaxies helps to hold the local group together, while those galaxies continue their cannibalism. The calculation of the gravitational limits of the local galaxies thus confirms theoretical conclusion from more general premises that the eventual result of the evolution process will be a giant spheroidal galaxy containing most of the mass of the local group. It is even possible that both M31 Milky Way galaxy may be swallowed by a larger, hitherto unrecognized member of the group. In page 231, galaxies of less than maximum size, such as the Milky Way, some of the pulsars originating in the outer portions of the central regions are able to make their way out to join the pulsars originating from isolated supernovae in the galactic disk. But there's no difficulty in accounting for the number of type 2 supernovae required in order to support the estimated pulsar population. Wow. Page 370, according to current estimates, the density in the core of the Milky Way galaxy is 30 or 40 times as great as would normally be expected, while the central regions of M87, the nearest and consequently the best known of the giants, are estimated to be at least 80 times the normal density. And page 371, this is our own Milky Way galaxy where we have the advantage of proximity and can observe details that would otherwise be beyond the scope of our instruments. A small region known as Sagittarius A, apparently located at the dynamic center of the galaxy, has some unusual characteristics which indicate that it is the kind of a core that we could expect in a spiral of modern age. Page 371. The existence in the core of the Milky Way galaxy shows that this galaxy has already developed the kind of an intermediate speed core, a white dwarf core that we would theoretically expect in a galaxy. Let me just say parenthetically, intermediate speed means speed between 1 and 2c. But that's not S over T, that's T over S. That's why outward in coordinate space is inward in coordinate outward in coordinate time is inward in coordinate space. That's why it's compact. Page 372, the existence of radiation of this nature identifies some Milky Way galaxies, one that has a good start toward the buildup of matter with speeds in the upper ranges, which will eventually lead to the kind of gigantic explosion that eject a quasar. Okay, well, that's pretty lengthy. All right, so that covers galaxies in the reciprocal system. Of course, I have here 622 galaxies. Let's just click Show All. And so we can just, like, here's Triangulum, here's Andromeda, for example, and so on and so forth. Anyway, that does it for today. Please study the reciprocal system and prove it for yourself for the simplest possible treatment. Please obtain my work, The Unmysterious Universe. Has all the concepts, many diagrams. It'll get you started on the theory. Then, if you do want all the mathematics, I mean all the mathematics, please obtain my work, my magnum opus, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. 711 pages in the PDF file, 711 slides in the PowerPoint file. It has thousands and thousands of equations, diagrams, tables, you name it. So it'll keep you busy for months and months. Now, once you're done with that, you should consider getting these two database modules. We've been covering here the Macrocosmos database, which has all the properties of the universe as a whole, galaxy clusters and groups, galaxies, star clusters, stars, planets, moons, minor bodies like comets and asteroids, nebulae and gas, and dust clouds and voids. Has a great graphing program, which we'll eventually show here on YouTube. It covers all the objects, not all the objects, but I mean all the classes of objects of the universe. So, and of course you can add whatever objects you want. Now the Reciprocal System Macrocosmos database you can see here. This has all the properties and calculations for matter and cosmic matter, or inverse matter. It covers photons, subatoms, atoms, compounds, and alloys. You can just see all the properties here: interatomic distance, valence, specific heat, energy entropy, thermal expansion, compressibility, electrical and magnetic properties, isotopes and spectra for solids. And for liquids, vapors, and gases, we have volume and density, specific heat, energy and entropy, viscosity and surface tension, electrical and thermal conductivity. We have photon properties, and of course we have cosmic elements and subatomic particles. Cosmic elements are called mesons currently by the conventional theorists and experimenters. Again, this has a great graphing package. Quantum mechanics is nothing like it. But we're not done yet. Doobie Larson was also a great theoretical economist as well as a theoretical physicist, and I've made his economics work computational, just like I've made his theoretical physics work fully computational. So my software package called Optimal Economist and Implementation of Larsonian Econophysics covers microeconomics of individuals and businesses and business sectors, and the macroeconomics of countries and regions. So completely supersedes Keynesian economics, just like the reciprocal system database and existence and interactions completely supersedes quantum mechanics and general relativity. All right, that wraps it up for today. Again, please study the reciprocal system and prove it for yourself, and thanks for your attention.